It seems very clear, does it not, that logarithms and exponentials are related. And the way they're related is, in fact, they are inverses of each other. Like subtraction and addition, one undoes the other. Squaring, square root, one undoes the other. It's the same relationship. Taking something to a power and taking logs, one undoes the other. In fact, you can see it here. 3 to the 5x minus 1, take the log, I get 5x minus 1. And our general notion for this idea of one function undoing another is in fact the idea of an inverse function. So let's talk about this in general, the idea of inverse functions. So here's our definition. It says, if I have two functions, and I shall call them f and g, because I'm not very imaginative, if I have two functions f and g, they are said to be inverses, or the inverse of each other, if for every x in the domain of g, f of g of x is equal to x, and g of f of x is equal to x. So this is our function notation, which we spent some time trying to get you used to handling, and obviously we're going to get some more practice here. And this is an equation. It says if I start with x, evaluate g at that value, then I evaluate f at the value of g of x, I end up back where I started from. One undoes the other, is what it's trying to say here. So these statements say one function undoes the other function. Undoes is fairly loosely used there. One function undoes the other function. That's the general idea. So let's get an example of this. It might make it clearer. In here, normally, well, what we've been doing a lot so far is I've given you the formula for a function and said to you, what's the largest possible domain? When we're talking about functions and their inverses, quite often we have to be careful it won't be on the largest possible domain, it'll only be on some specific part of the domain. So it's very important when I'm talking about function and inverses that I also specify what domain I'm working on. So in this case I'm going to say let f of x be the function x squared whenever x is positive, and let g of x be the square root of x when x is positive. So I've actually explicitly given you the domains of the function sitting here. Now, let's get used to this notation here. So let's choose a value for x, and I'm going to choose one where the arithmetic is easy. So I'm going to say for x is equal to 16. I want to work out f of g of x. So here we go. F of g of 16. Now, if these are inverse functions, then this number here should be what I started with. It should be 16. That's what that's saying. That should be 16. So let's have a go at it. G of 16. G is the square root of x. So g of 16 is 4. So I can say this is f of, now g of 16, that's the square root of 16. So that's f of 4. Now, evaluate my function f at 4, and that is 4 squared, and I end up back at 16. So f of g of 16 is 16. That is good. I started here, so that's my first equation is satisfied. F of g of x is x. The next thing I should check is g of f equal to x. Now, 16 turns out to be too big a number for me to work with. I can't work that out. So let me do one I can do in my head. Let me choose, say, x equal to 4. And now let me go g of f of 4. And if things are well, I should end up with this number here being 4. The number I put in is the number I should get out. And I do it in stages. I work out f of 4 first. And you can see here we had f of 4 was 4 squared. So that's g of 16. G of 16 is the square root of 16. So I come back with 4. And so the number I put in is the number I get out. So that says these two functions are inverse functions. Well, I should be a little bit more careful on that. It worked for these two choices of x. Does it work for every choice of x is what I've really got to check. So I better do this more generally. So I better say here, in general, let x be some number a where a is a positive number. So let's work this out in general. And I'll start with f of g. F of g of a. If these two functions are indeed inverses, one undoes the other, I should end up with a. So g of a is the square root of a. So that gives me f of the square root of a. Now f is x squared, and we know from our function notation, everywhere I see x I have to put the square root of a. So this becomes the square root of a, all squared, which is just a. So it says no matter what number I start with, f of g of a gives me a. That's good. I then need to check the other way around. I then need to check that g of f of x is x. So let's do that one as well. So g of f of a. In there. F of a is a squared. So I need to calculate g at a squared. And that gives me the square root here. G is square root of x, so that's the square root of a squared. This is the positive square root, so I just get back a. And so we conclude that f and g are inverse functions. One undoes the other. So f and g are inverses of each other. Inverse functions come in pairs. Of each other. The idea of inverses, of course, is really important when you try to solve equations that have functions in them. Because this is what we did here. We're going to see that exponential functions and log functions are inverses, and when I see an exponential, I use its inverse to make x the subject. Okay? Likewise, when I see x squared, I take the square root of both sides. I'm actually using the inverse function each time in there. Interestingly, inverse functions are quite often denoted by f to the minus 1x. And this is just put in here to confuse the heck out of you. It's actually, this is a leftover from the history of maths, in that as new mathematical ideas come on board, whoever gets to make up the idea quite often makes up a notation that goes with it. And somebody somewhere had made up this notation for inverse functions, and that stuck. Even though we would usually do this, f to the x to the minus 1, we would normally interpret as 1 on f of x. So what we're going to say is this f to the minus 1x is different to fx all to the minus 1. Unfortunately, as I said, that's just a quirk of the history of mathematics, that this notation has stuck and we've never changed it. So we're just hoping that you are clever enough to work out from the context that yes, this is what you actually mean, not this. So note in here, f to the minus 1x is not the same as fx all to the minus 1. This one means the reciprocal, this one means the inverse. In there. Okay, so it says, find the inverse function now of fx as x squared, but this time let's choose a different domain. Let's choose x being negative rather than positive. We saw over here that the inverse whenever x squared was positive was the positive square root. So I guess we can make a pretty quick guess and say the inverse is going to be the negative square root. I think that's what would undo it. For example, if I took minus 2, squared it, I get plus 4. To undo, I'd have to take not the square root of 4, but the negative square root of 4. So I get back to minus 2. All right? I need to get back where I started from. So I think I know the answer already. I think the answer is going to be the negative square root is going to be my inverse function. But we can do it algebraically if we're clever. So I'll go like this. I want to find an inverse function, which I shall denote by f inverse x, and I want this function to satisfy f of f inverse x to equal x. That's our definition. That's what we know an inverse function does. The function undoes the inverse function. And to make this easier, rather than having that whopping big notation in there, I'm going to do this. So I'm just going to say let f inverse x, I'm going to write y instead of f inverse, just because it's quicker to write.
In that first line, is it meant to be x squared again, or is it just x?
X, because it says here, for every x in the domain, when I apply my x to the first function, then to the next function, I get back the number I started with. I get back to x. Okay? Now, just so happens I'm going to be doing some squaring and stuff in there, but that might or might not be the case, depending on what f and g are. Okay? So, yeah, you can imagine that that's that statement where I've got f inverse instead of g. I've just used the different notation sitting there. So here I go. I want f of y to give me x. Now I know my function, it's x squared. So f of y is y squared is equal to x. I want to know what y is, so I'm going to make y the subject of that equation. So I am going to undo squaring. And so I'm going to say y is equal to, now I've got two choices here. I've got the positive square root and the negative square root. And since my domain is less than 0, I will want an answer that is less than 0, so I will take the negative square root. And I've done that because the domain, now this is a little bit confusing, but the domain of f is the set of all x such that x is greater than 0. So I want an answer that is less than 0. I want an answer that is less than 0. So sitting in here, I can actually draw a picture of my function and its inverse. So let me just draw this picture here for a bit. X squared. I can't do parabolas round the right way, so let me just dot it in. Right, so there's my graph of x squared. We only want this portion of it. There. So that is y is equal to x squared on x is less than 0. So that's my function. The inverse function comes around like this. Here and here. Like that. And we only want this portion of it. Like that. And so this one is y is equal to the square root, negative square root of x, sitting there. So there is the graph of the function, and there is the graph of the inverse function. And let's just do it. If I started at minus 2, here I would go up to 4. F of minus 2 is 4. I come to 4. F inverse of 4 is minus 2. Which is what I started with. I started at minus 2. Likewise, if I went the other way around, if I started here at 2, I'll start at 4. 4 is easier. Come down, minus the square root of 4 is minus 2. Go to the function, minus 2 is 4. So I come back to where I started. Started at 4, finish at 4. So these are indeed inverse functions. So, I said here algebraically to find the inverse function. I mean, you can do these via common sense, I guess. But if you want to be systematic, then using this formula here is probably a good way of doing it. And to highlight that, so I've actually said here, we want to find f inverse such that, so here it is. Here's again, this is my algebraic way of trying to find the inverse. I mean, let me just use common sense to start with. If I've got a function, it says if I give you a number, I've got to multiply by 2 and then add 3. So to undo that, I'd have to subtract 3 and then divide by 2. So the inverse function is going to be x minus 3 on 2. Right? Just use common sense. But there are functions for which common sense is harder to work, and sometimes we just prefer to use an algorithm rather than common sense anyway. Okay, so let me use this. So here we go. So let y be f inverse x, and then my equation here says I want to find y so that f of y is equal to x. In this case, function y, my function is 2x plus 3. And so everywhere I see x, I have to put y. So I have 2y plus 3 is equal to x. Make y the subject. And here I'll have y is equal to a half of x minus 3. Oh, x minus 3 on 2. And I guess I would write that as a half x minus 3 on 2, simply because I recognise that as a linear function with slope a half and y-intercept minus 3 on 2. And so I can draw my graphs of both the function and its inverse in here. I guess I should finish that off by saying f inverse x is a half x minus 3 on 2. And in here, the domain will be all real numbers. We know that for a linear function, we can find the value for all real numbers. And so somewhere here, I should be able to make myself a graph. So the graph of the function itself, the function was 2x plus 3, so that has a y-intercept of 3 and a slope of 2. So every time I go down 1, it'll go through there. So if I join that up, oh, look at that. Got a bobble on the thing there, but it doesn't matter. That's y is equal to 2x plus 3. And for my inverse, it has a slope of 1/2 and a y-intercept of -1.5. So there, and I'll go there. And if I can get my ruler to work here, it'll look something like this. So that would be y is equal to -1/2 x minus 3 on 2. So there's that one. And there's that one. So what, have you worked out the symmetry for me? You picked it. You said there's some sort of symmetry sitting there. Yeah. Yes, indeed. It's certainly got something to do with 45 degrees. I'll do one more and then we'll come back.
4y equals -1/2 x. Shouldn't the slope be the other way around?
Shouldn't the slope be what?
4y equals -1/2 x minus 3 on 2. Isn't that a positive gradient?
Oh, 1/2 x. Yeah, I just wrote that wrong. Yep. So yeah, good point. Yes, it should be a positive gradient. So we've done a linear function there. Now let's go to our exponential functions. So, let me, even before we start, we know what our exponential function looks like. It goes like this. It goes through there. 2 to the 1 is 2. 2 squared is 4. So that's our graph of our exponential function sitting there. That's y is equal 2 to the x. And of course, that gets steeper and steeper as we go. So there's my function. I want to find the inverse function. And so using the same method as before, I'll say let y equal f inverse x. And so I want to find y such that f of y is equal to x. So that the number I start with is the number that I finish with. Now in this case, function y, everywhere I see x I have to put y, so this function y is 2 to the y. So 2 to the y is equal to x. I now want to make y the subject of that. And we saw before that the logarithm function is the one that I want to use. So I'm going to use log to the base 2. Here of 2 to the y is log to the base 2 of x. And so what power must 2 be raised to give 2 to the y? And the answer is y. So y is equal to log 2 log base 2 of x. And that is my inverse function. So therefore, f inverse x is log x to the base 2. So the inverse of 2 to the x is log to the base 2. If I had 3 to the x, the inverse would be log to the base 3, and so forth. I can make a sketch of this log graph. We did one of these last week, but let me just do it by putting in a few points. First of all, I know the domain is positive values of x, and I know that if I put 1 in there, what power must 2 be raised to give 1? It's 0. So it goes through 1, 0. What power, if x is equal to 2, what power must 2 be raised to give 2? And the answer is 1. So it goes through the point 2, 1. If I've got 4, what power must 2 be raised to give 4? It's squared, 2 squared, and so on. So the log graph will look like this. That will be my graph of log x to the base 2. That's not exponential, that's logarithmic. Okay, that is in fact, we would say that's a logarithmic curve.
So even though
It's the inverse
of the
exponential function. So this is an exponential function, this is a logarithmic function. They are inverses of each other, and the graphs are related. Let me just come over the page and we'll bring it out. So the graphs are reflections in the line y is equal to x. So the graphs always turn out to be that. So if I have a function and its inverse, then they're reflections in the line y is equal to x. And in fact, what I might do is I'll just put that one on this side, and I'll go back and do these in here. So that's what we'll work towards. That's what we've got. And let me just put in y is equal to x in all of these. That goes through there. So that's the line y is equal to x sitting there. And you can see that does look like a reflection if I've drawn my picture correctly. And because these two functions are reflections of each other, the domain of one is going to be the range of the other, and the range of this one, y greater than 0, is going to be the domain of that one. So let me just say here, note, I'll put it up here, note, the domain of f is equal to the range of f inverse, and the domain of f inverse is the range of f. And that's true for all your inverse functions as well. So let me just write that down explicitly here. So for example, the domain of my exponential function, the domain of f is all real numbers. I can calculate 2 to the x for any value of x. The range of f is the set of y values such that y is positive. They're the values there, that's the range. You can see that for every positive y value there's a point on the graph. Let's go now for the inverse function, for the log function. The domain of f dash is the set of x values such that x is positive. So that's the same as the range of f. And the range of f inverse is the set of all real numbers. That gets bigger and bigger and bigger, albeit very slowly. And so you can see the range and the domain there are the same. Range and domain are the same there. And that's a consequence of the fact that these two are reflections in the line y is equal to x. And of course y is equal to x, it makes 45 degrees, doesn't it? That's where your 45 degrees comes from. And so if we were to go back, so I'll put that one there. If we go back to this one, I could quite happily put in y is equal to x on here. Let me put it in. Get something like this. So there's the line y is equal to x, and they do indeed look like they're reflections across that line. You can imagine that one flipping over to that one, and vice versa. The domain and range of these are all real numbers, so they're naturally going to be equal on that one. And if we go back to the earliest one we had. So there's that one. In this one, again, here's y is equal to x sitting in here. You can see that x squared and minus the square root of x are reflections. And in fact, you can also see in here the one that we had right at the very beginning of x squared being positive and the inverse being the positive square root of x. They're also reflections sitting in there. So I've actually got the example before sitting in there as well. But once again, look at the domain of this function. The domain is the set of x values less than 0. The range of this one, the set of y values less than 0. The range, set of y values that's positive. The domain, set of x values that's positive. Okay, so there we go. So that's the idea of inverse functions, and as I say, inverse functions are useful for when we try to solve equations that involve these sorts of functions.